Okay, guys, let's just see what you did. Let's confirm that you remember what we did yesterday. A1, let's see, Jeremiah, what'd you get for A1?
1/2.
Awesome, you plugged in 1 for n, and that simplified to 1/2. Nice. Catherine, can you tell me what you got for A2? Yes, plug in 2 for n, and we get 2/3. And Charlie, can you tell me what you got for term 3?
3/4.
Nice. Okay, so that's review from yesterday, and then what we stopped with yesterday is how can you generate a formula that works for any term. And remember what I look at, or what's good to do as you're looking for these formulas. You want to take a look at how was the term generated from the nth value. So for example, this term is A1. That means n is equal to 1. This term is A2. That means the number we're looking at is 2. This term is the third term, it's A3. So the value of n is 3, and this term is the fourth term, telling us that n is equal to 4. And we want to see how can we work with the value of n to generate each term in this sequence. So this one's probably the most basic. What would be the formula that would generate each term in this sequence? 2n. I know we visited that a little bit yesterday. But now with your partner, see if you can complete numbers 2 through 5. 2 through 5. All right, guys, I've got some Jolly Ranchers up here. For you and your partner, let's see what you got. Raise your hand if number 2, you were able to generate each term. Nate.
Like, generate each term?
Like, I mean, what was the formula?
Oh, I was like,
sorry.
N squared.
Nice. I'll give this to you in a moment. Somebody else, the third. What's happened in the third one? Lauren. N plus quantity, n minus 1, over 2n. Let's see, n plus quantity of n minus 1. Yes. I had it as 2n minus 1. But yeah, that's exactly right. Nice. Now, a lot of people were struggling with this one, number 3. And really what's happening in the numerator are their odd numbers. And if you're looking at odd numbers, you want to take a look at, odd numbers are generally represented as, actually guys, this is something great to write off to the side just because odd and even values show up all the time. So notice that Lauren was generating the odd number in the numerator. Odd numbers are generated with the formula 2n minus 1 or 2n plus 1 versus even numbers are generated with the formula 2n. That's just something good to remember. It might show up in your homework. It might show up on the quizzes or tests. That type of pattern shows up a lot with sequences. Okay, how about the next one? Can someone raise their hand and tell me how did you generate, or what was the formula? Olivia. N cubed. Excellent. Nice. And how about this last one? Charlie.
I had -1 to the n times 2 to the n.
-1 raised to the nth power, perfect. Notice this right here generates every other term as negative. Why do we want to think about -1 raised to a power? Well, when -1 is raised to an odd power, it stays negative, versus when -1 is raised to an even power, it becomes positive. So that's why Charlie had -1 to the nth, and then he noticed that each term could be looked at as 2 to the first power, 2 squared, 2 cubed. Oh, did you guys think I was done?
Yeah.
Yeah, you were all giving me weird looks, and I was like, I don't know what I'm doing here. Okay, 2 to the first, 2 squared, 2 cubed, 2 to the fourth, 2 to the fifth. Excellent. All right, I got to give you 2, and who was the other 2 that got it? Olivia. Okay. All right, this is another thing to be aware of that comes up again and again. To generate every other odd term, or sorry, every other term negative. Every other term negative. And I know we discussed this a little bit yesterday, but you will want to use either -1 to the nth power or -1 to the n plus 1 power, depending on which terms appear to be negative. Okay, that's good review for from what we learned yesterday, and there were a few more for you to practice. And before I come around with these Jolly Ranchers, I want to introduce you to looking at each sequence and turning it into something which is called a series. A series just takes the terms in a sequence and adds them up all together. We have a very famous math story about, and the reason it's famous is because this mathematician named Frederick Gauss, he determined what the numbers, this is legend, but he determined what the numbers of summing from 1 to 100 were when he was in kindergarten. This is how the story goes. Supposedly this little Frederick was just causing chaos in kindergarten, and the rumor had it that he was bored. And so his kindergarten teacher just got frustrated with him, was trying to keep him busy, and said, Frederick, please, can you just go in a corner, count up all the numbers from 1 to 100? Now, most kindergartners would look at it and go 1 plus 2, okay, 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 4 is 5, and obviously that would take a kindergartner, even a bright kindergartner, a very, very long time. Frederick, he noticed something different. He thought in terms of all the numbers listed out. And he said, if I think about the numbers of 1 to 100, there's a pattern that occurs. Specifically, if I add the first term plus the last term, and then I look at the second term plus the second to last term, and then I look at the third term plus the third to last term, and the fourth term plus the fourth to the last term. Well, let's see if we can determine his pattern. What is the first term plus the last term? 101. What's the second term plus the second to last term? 101. What's the third term plus the third to last term? 101. Obviously, this pattern is continuing. So he's a very bright kindergartner. He's a mathematician. We have many formulas from him. His name was Frederick Gauss. How could he determine what they all added up to fairly quickly? Yes, take 50, multiply it by 101, and he got the answer to be 5,050. So legend has it, as he comes back to his kindergartner teacher within a matter of minutes and goes, maybe it was seconds. The legend is kind of differs now because this was a really long time ago. But comes back to her and says, it's 5,050, teacher. And she had to like check and actually manually after school add up all these numbers. And then she was just like, this kid's brilliant. Yes, 5,050. That actually happened. Yeah, we don't, the legend says kindergarten. Some legends say first grade, second grade. But the thing is, he was young, like really, really young, elementary school. So we have a summation formula from him. And we're going to be focusing more and more on that formula in the future. But what was illustrated to you here is what is a series, or what is summation represented as. Summation notation is a concise way to represent adding all the numbers in a sequence. Here's what it looks like. Well, if we were just using the kindergartners, I call it the kindergartners formula, but Frederick Gauss's formula, what would be the formula for each term? Like if I looked at this as 1, 2, 3, 4, 5, 6, and so forth. What would be the formula that's generating each term? Well, it's just the value of n, right? When n is 1, it's 1. When n is 2, it's 2. When n is 3, it's 3. When n is 4, it's 4. So this new notation that we look at when adding up all of the terms, it looks like an E. It's called a sigma. It's a Greek letter. And this sigma notation says you can start with the first value and end at the top with the last value. So we're summing the numbers from 1 to 100. And then your formula that generates each term goes right off here to the side. So what was represented by what Frederick Gauss did looks like this in summation notation, where you look at what you start with here. We start adding the numbers from 1 to 100, and you plug it into this formula. So this is the formula that makes each term. I always say generates. I don't know if that's weird, but the formula for each term. Yeah. This is just representing what the notation is for what Frederick Gauss did. Yeah, write it down and then we'll define it. But basically, when you look at something like this represents all the numbers from 1 to 100 out. So the answer to this is equal to 5,050. 5,050. So this is the new notation that we're going to become more familiar with for the rest of today's lesson is summation, when you're adding up the terms in a sequence. Whenever we take a sequence and start to add the terms together, this summation can be called a series. You're adding in between. And mathematicians came up with a concise way of expressing sequences so that every term would not have to be written down. So rather than writing out the numbers 1 to 100, this is a more effective way that math teachers found to represent what the kindergarten teacher made Frederick do. Just she made him sum all the numbers from 1 to 100. So that's what we're looking at. What is a concise way to represent those types of patterns when you're adding the terms together? So this is the explanation, or this is what we're going to be visiting today. This little E symbol, that represents adding together. Adding together. The number at the bottom tells you where to start. Whew. So this is where to start. The number at the top will tell you where to finish. And then whatever goes here is the formula for each term. Formula used to generate each term. So let's see how we would look at this in an example. For example, number 1, it says find each sum. So this right here tells us how to generate each term. What number are we going to start plugging in for K? 3. So we're going to start plugging in at K equals 3, and we're going to keep counting upwards until we reach what? Sorry. Until we reach 5. Now, to determine what the actual terms are in the pattern, I plug in each value of K into the formula. So what I'm looking at is I'm summing together 1/3 plus 1/4 plus 1/5. And then my answer is that sum. This is summation notation. It's just like the answer was 5,050 for Frederick Goss. So what would we need to do here in order to add this together? Common denominator. What's the least common denominator? 30? Isn't it 60? 60? Okay, good. So we'd multiply this by 20 over 20. This one by 15 over 15. This one by 12 over 12. And we add those together. 20 plus 15 is 35. Plus 12 is 47. So 47 over 60 would be this summation. Okay, I know that's new, and I gave you kind of a fun story, which we will be repeating when we look at specifically arithmetic series, adding numbers together. But for now, practice that new notation. Practice number 2 and number 3. 2 to equal 426, number 3 to equal 12. Give me a thumbs up if you got that. Yes? Okay, let's make this just a little bit more advanced. What if I give you, just to kind of really drive this home, add a number 4 and a number 5 off to the side. What? Because, oh, I was getting it. Don't make it.
My space, so like...
Oh, got you. Sorry. Okay, so if I give you this, and I say you start with I is equal to 3, your formula that's generated is I squared, and the terms are 9 plus 16 plus 25. If I ask you, what would have to go here?
3.
Would it be 3?
Oh,
I'll be 6.
Would it be 6? Well, let's think about this.
It'll be 5 because you include 3.
Good. It would be 5 because you have 3 squared, 4 squared, 5 squared. So be careful here. Sometimes people say, oh, 6 because there's 3 terms, but you have to take into consideration that you're plugging in this number. So this would actually stop here at 5. Okay, let's try, let's see, I want to do just one more in here. Let's do the most advanced type that you could see. So go ahead, write number 5. Sorry, I should have added these into the notes. But you don't have space? Oh no. How about at the end? Can you add at the end? So let's say that we have something like, let's do this. Let's do n is equal to 1, and it's going to end at 5. And your elements are 1 plus 8 plus 27 plus 64 plus 125. Can you use that information to generate what would have to go as the formula for each term? What is it? Good, n cubed. Okay, so that's just the different ways you could see the summation being given to you. Either you have to find the sum, you have to find a missing part of the summation, or you might have to find the actual formula that generates the terms. Any questions on that so far? Okay, let's consider then, what about the next sequence that's given to you? 1/2 plus 1/4 plus 1/8 plus 1/16. If we were to add these numbers, notice the dot, dot, dot means that the sequence is continuing forever and ever. If we were to add these numbers, so turn this sequence into a series, remember that's adding the numbers together, what do you suppose would be the sum? So if I was saying add these numbers to infinity, well, first of all, what's happening in the denominator? It's 1 over, how can I make the formula for each term? 2n, because this is when n equals 1, it's 2. When n equals 2, it's 4. When n equals 3, wait a minute, doesn't work, because 2 times 3 would give me 8. So how would I look at it? 2 to the n. Excellent. So 1 over 2 to the n. Now let's go ahead and let's take a look at, I want to see if we can determine, even though this sequence goes on to infinity, so you're adding 1 over 16 and then 1 over 2 to the 5th, 1 over 2 to the 6th, 1 over 2 to the 7th, 1 over 2 to the 8th. Is there a way that we can determine what the sum will be, even though we don't, the amount of terms is infinite? Well, let's take a look at this as in terms of a partial sum. So this is new notation to you. We're going to focus on it more in the future. But basically what this looks like is you're looking at the sum of n represents the number of terms. So for example, S1 is, let's see, what's the sum of the first term? So of just one term, 1/2. Yes, it's just 1/2. We don't add anything to it. How about the sum of the first 2 terms? 1/2 plus 1/4 is, yes, 3/4. How about the sum of the first 3 terms, which would be 1/2 plus 1/4 plus 1/8? Doesn't matter what? It's the first. So S sub n is the number, so the first number of terms. So like if it's the first 2 or the first 1. Yep. So the first number of terms. So the sum of the first 3 terms, what did that come out to be? What's 3/4? Good, 7/8. How about the first 4 terms? 1/2 plus 1/4 plus 1/8. Yes, we're adding, or plus 1/16. So we're adding 14/16 plus 1/16 gives us 15/16. And the sum of the first 5 terms, which is 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/25, no, 32, thank you, is equal to, well, we can multiply this by 2 over 2, yep, you get 30 over 16 plus, or I'm sorry, 30 over 32 plus 1 over 32 would give us 31 over 32. So, well, here's the question. Katie, Olivia, can you guys put those away? Here's the question. If we think about regarding this sequence, if you let the number of terms go to infinity, so if we're looking at the sum of infinite terms, would the sum go to infinity? Let's see, the sum of 1 term was 1/2, the sum of 2 terms was 3/4, 3 terms was 7/8, 4 terms is 15/16, sum of 5 terms is 31 over 32, What do you think the sum of like 100 terms is going to equal?
Under 1.
Well, it's going to be a fraction, right? It's going to be a fractional value. Here's how we can think about it. If I take a look at this as a whole, think about a whole box. You guys remember back to elementary school when you were looking at fractions in terms of pieces of a picture? If I add a half, so if I look at the sum of 1, if I add a half, that's the sum of the first term, 1/2. What's the sum of 2 terms? A half plus a fourth, right? So could I split this half in 2, and that would be 1/4? So this would be 1/2, this would be 1/4, so I'm taking 1/2, and I'm adding a fourth to it. And now if I add an eighth to it, how much of this part would be an eighth of the whole? Half of it would be an eighth. So that's the summation of 3. That's the first 3 terms. If I add a 16th to it, what would I do to this box? Half it. Now if I add a 1/32 or a 32nd of it, what would I do to this box? Half it, so that's 1/32. How do I add 1/64? Half it. And then 1/128 is half of it. As I continue to add to infinity, what is the actual sum going to? 1. Exactly right. So the sum of this sequence would, when going to infinity, is becoming closer and closer to 1. So we're going to take a look, and this is not today, but we're going to be looking at how some series can diverge to the answer of 1, because you can see it as we add a half of a box plus a fourth of a box plus an eighth of a box. You're summing to equal the whole square, the whole box. So the sum of the sequence is getting closer to 1, to the value of 1. Or you can think 1 whole. Okay. All right, now try your hand at the following. See if you can go back to using the summation notation. That's going to be our main focus today, the EGAI. Summation notation is the EGAI. With an index beginning at 1. Just so you know, the number at the bottom, that's your index. I didn't want to throw too many terms at you at once, but we can go back here to that summation notation and just go ahead and put where your start, that's your index. Okay, so see if you can create the summation. You don't have to solve it, no. Just create the summation. Try the next one. Are tough when you first look at them. This is a practice makes perfect type of lesson where you just keep working with the numbers till you start seeing the patterns that make sense. Like this one, I can get fairly quickly now. This is like my 9th year of teaching college algebra. My first year, I spent an hour at the dinner table trying to figure this one out. But now I can look at it, and even though I haven't taught this lesson for a year, I can remember, because of that struggle, of, oh yeah, I need to remember that if there is no x, I need to think about x to the 0 power, because x to the 0 is 1. And then generating every other term, I think about -1 being raised to n, or n plus 1. And then I can see the coefficients in front. But I just want to encourage you, if you didn't see that right away, don't let that throw you. You will get better at it. The more you work at this, you will get better at it. Okay? But were there any questions about how this actually worked? We want to see it like played out. When n is 1, -1 to the 1 plus 1 times 1 raised to the x to the 1 minus 1 gives us +1 times 1 times x to the 0. So that's our first term. When n is equal to 2, we get negative 1 raised to an odd power, which will keep it negative, times 2 times x to the 2 minus 1. So that gives us negative 1 times 2 to the x. And that's where you can see that second term in the series. Does that make sense how that works?
Yeah.
Okay.